Hello, scholars. Welcome to Lesson 13, Session 4, on determining when a system has zero or infinitely many solutions. So we're just going to put together a couple ideas now. In Lesson 12, we talked about how many solutions a system of equations could have. No solutions, infinitely many, or one solution. Now we're going to apply that using substitution because right now it's not easy to tell, right? Looking at these equations, I don't know. They look awfully different. I wouldn't imagine if I approached these that I would be considering that they would have zero or infinitely many solutions. So if I was just told to solve this system of equations, I'd be like, okay, well, I know how to do substitution, so I'm going to do that. Now, if we're going to do substitution, then we are going to need to have a variable all by itself, right? And so you're going to need to make a decision here. You can solve for y or you can solve for x because neither is solved for in either of these equations. So you need to do a little bit of prep work, okay? Now, I see that it would be really easy to solve for y in this equation, but I need to make sure that I get it so y is all by itself. I'm going to do that. And I see that solving for x here would be really easy as well. So it's kind of like your choice. I'm just going to jump into this equation right here. I'm going to write it down over here. Negative 1/2 x plus y equals 3. And I just want to get y all by itself. So how do I do that? Well, I need to get rid of this thing. This is negative 1/2 x. So I'm going to do the opposite. I'm going to add 1/2 x to both sides. And that's going to go away over here. I'm just going to be left with y, just like I want it to. And over here, I've got this 1/2 x plus 3. Now, you might ask, why didn't I put this together? Well, that's because they're not like terms, okay? So they can't go together. This has an x. This does not. Okay, now y is all by itself. So I'm going to circle y. I'm going to box its definition, and I need to bring this on over the other equation, right? I used this equation, so I need to bring this over to the other equation and drop it in right where I see y. Now, I'm ready to rewrite my equation, so I'm just going to rewrite it exactly how I see it. X minus 2. Stop. I got to y. I know what y is, so instead of writing y in parentheses here, I'm going to write 1/2 x plus 3, and then continue, equals 4. Now we're going to use our 5 steps to solving any algebraic equation now that I have an equation that only has one variable in it. If it's got more than one variable at this step, you did something wrong. Okay, so I'm going to distribute. Boop, boop. Okay, here we go. So we still have this x. This is negative 2 times 1/2. Half of negative 2 is negative 1x, of course. And negative 2 times positive 3 is negative 6. This still equals 4. You should be screaming, oh no, Mr. Gibbs, something really weird happened. X minus x is nothing. Those cancel each other out, and I'm just left with negative 6 equals 4. Well, that's not true. My x's went away, and I'm left with a false statement. A false statement. And you might be saying now, Mr. Gibbs, I know what the answer is because we already did this with regular equations. Whenever our variables go away and we're left with just a false statement, it's no solution. And I would say right on. That is exactly what's going to happen. It's super similar here when we have a system of equations. We just need to make sure we don't make the simple of mistake of saying that because I get confused, it's no solution. It needs to be super clear that your variables canceled each other out if you're going to say it's no solution or infinitely many solutions. So I want to take a note of that. If variables cancel out and you are left with a false statement, if variables cancel out and you're left with a false statement, the system has no solution. Notice, that's not true. -6 does not equal 4. The variables went away. No solution. If variables cancel out and you are left with a true statement, for instance, if this would have been like 4 equals 4, right? If we would have been left with 8 equals 8, if it would have been true, the same number on both sides, the system has infinitely many solutions. Meaning that it does not matter what number of an x I would plug into this equation, the y that goes with it in the other equation is going to be the same x and y that go into the first, and then you can find another x, and the y that goes with that is going to work in the other equation because they're exactly the same equation, right? So these are some big ideas, and I'm not gonna leave it at that. We're gonna play with that idea a little bit more together. I just wanted to get us started, and this remind you, this is so much like what we did together when we solved equations, right? And the variables went away. Most of the time, though, we are going to get only one x and one y that are going to be a solution to a system because it's where the two lines meet, right? It's where the two lines meet. If I've got no solution, I've got parallel lines. And if I've got infinitely many solutions, well, it's the same line. It's the same equation, just maybe written differently. Okay, you should know what to work on next. And thank you for your hard work.